Welcome along to the deep dive. We know there's a ton of specialized knowledge out there, and figuring out how to navigate it fast is, well, key. That's exactly why we're launching this brand new series, our dedicated CSWIP 3.1 exam prep series. Our mission today, pretty clear. We're diving into some crucial multiple choice questions, the kind you'll likely see on the CSWIP 3.1 Welding Inspector Exam. But we're not just going to give you the answers. No, we'll break down the question, talk about the right choice, and really get into the why behind it. Hopefully give you a few of those aha moments.
Exactly. Just memorizing answers won't cut it for real competence in welding inspection. You really got to grasp the principles underneath. So think of this as less about just passing the exam and more about sharpening your thinking for when you're actually out there on the job. Understanding why connects the dots.
Absolutely. And we'll do our best to make even the trickier concepts feel straightforward. By the end, you should feel well equipped, definitely more confident, ready to jump in.
All right, first question. This takes us into friction welding. Listen up. In friction welding, the metal at the interface when the joining occurs is described as being in the yi. And your options are A, liquid state, B, intercritical state, C, plastic state, D, elastic state. Have a quick think. Okay, got your answer. The correct answer is C, plastic state.
Yeah, plastic state. And this is really fundamental to friction welding. It's what makes it a solid state process. So unlike your typical fusion weld where you're melting metal, here you're rubbing materials together under, well, pretty high pressure. That friction generates heat, but it's very localized right at the interface. It softens the metal, makes it plastic. Think of it like really, really stiff clay. Crucially, though, it doesn't melt. No liquid phase. That's the key difference. It allows atoms to bond across the interface under pressure without all the issues you get with melting and solidifying. Okay, plastic, not liquid. That distinction feels important. But for an inspector, on a busy site, does knowing that really change what they do day to day, or is it more like background theory?
Oh, it absolutely changes things.
Yeah.
Massively. If you don't get that it stays plastic, you might be looking for the wrong things. You might be searching for, solidification cracking, or maybe gas pores, defects common in fusion welds.
Right. Yeah.
But you won't find them here. Instead, your focus shifts completely. You're looking for issues specific to solid-state joining, things like maybe an incomplete bond if the pressure or temperature wasn't quite right, or maybe issues with the flash that material squeezed out. It dictates your whole inspection strategy, what defects are even possible, saves you looking for ghosts.
Okay, that makes perfect sense. Knowing the process dictates the potential problems. Got it. Right, moving on. Next question shifts to heat input, specifically how welding position affects it. The question: the highest and lowest heat input positions are considered to be options A, PB highest, PA lowest, B, PE highest, PT lowest, PD highest, PB lowest, D, PF highest, PG lowest. All right, what do you reckon? The correct answer here is D, PF highest, PG lowest.
Okay, so heat input, it's a really critical variable in welding. Massively impacts the final structure, the properties of the weld, and importantly, the HAZ, that heat-affected zone next to the weld. Now, PF, that's vertical up welding. PG is vertical down. With vertical PF, you're generally forced to travel slower. You see, you're fighting against gravity, trying to keep that molten weld pool from dripping or sagging.
Right, takes more control.
Exactly. Slower travel means the arc is heating one spot for longer. More arc time per inch, basically. Result: higher heat input. Conversely, vertical down. BG gravity is actually helping you. It pulls the filler metal down.
So you can move faster.
Much faster, usually. Less arc time per inch of weld means, lower heat input. It's quite a difference.
So, okay, let's connect that. If an inspector sees PF specified on a WPS, should they immediately be thinking, okay, higher risk of, say, distortion or maybe some undesirable grain growth because of that extra heat? And for PG, maybe they're thinking, need to really double check for lack of fusion because they might have traveled too fast. Is it that direct?
You've absolutely hit the nail on the head. That's precisely the kind of thinking it enables. An inspector uses the WPS, the Welding Procedure Specification, as their roadmap. If it says PAF, they know higher heat input is inherent. So yes, they'll be more vigilant about issues linked to high heat, maybe checking for excessive distortion, looking closely at toughness test results if required, considering grain size. For PG, the concern shifts. Lower heat input, faster travel. The risk of moving too quickly and not getting proper penetration or fusion becomes more prominent. So they'll scrutinize the weld profile, maybe pay extra attention to the root, look for signs of cold lap. Knowing PF versus PG helps them anticipate and prioritize.
That's a really practical application of understanding the positions. Great. Let's move to question 3. This one is about NDT non-destructive testing, specifically radiography. A penetrometer, IQI, is used to measure the options. A, the size of discontinuity in a weld joint. B, density of a radiographed film. C, degree of film contrast. D, quality of the radiographic technique. Take a second. Okay, the answer is D, quality of the radiographic technique.
Right. An IQI image quality indicator, people often still call it a penetrometer. It's a standardized little device. Might have holes of different sizes or wires of different thicknesses. You place it on the part right next to the weld, usually, during the X-ray exposure. Its job isn't to measure the size of a crack or pore you find later. That's what the inspector does when interpreting the film. And it's not really about the film's overall darkness, the density, or how sharp the contrast is either.
Yeah.
Those are more related to the film processing. No, the IQI's whole purpose is to demonstrate that your technique, the X-ray settings, the source to film distance, all that setup stuff, was actually good enough, sensitive enough. If you can clearly see the required small hole or thin wire on the IQI image on the film, it basically proves your radiographic camera was capable of seeing a flaw of about that size if one was present in the weld. It validates the test sensitivity.
Okay, so it's like checking your eyesight before you try to read the small print. But what's the actual risk? Say the technique wasn't good, the IQI isn't clear, but the inspector looks at the weld image anyway. What could they realistically miss?
Well, the risk is huge, frankly. If that IQI isn't showing the required sensitivity, it means your whole radiograph might be unreliable. You could easily miss critical defects. Things like fine cracks, maybe some subtle lack of fusion, tiny porosity clusters, flaws that might not be immediately obvious on a poor quality image, but could absolutely lead to failure down the line. An inspector has to confirm the IQI sensitivity first, before even looking for flaws in the weld image itself. It's the baseline. If the technique quality isn't proven, you simply can't trust the inspection results, whether you see something or not. It's not negotiable, really.
That really drives home why it's step one. Foundational. Okay, let's switch gears again. Question 4 is about preheating steel. Preheating a steel plate with a carbon equivalent of CEV of 0.48 may be required to. Options. A, drive moisture from the plate. B, prevent excessive hardening in the HAZ. Prevent the formation of carbides. D, improve the mechanical properties of the weld metal. What are we thinking? The answer is B, prevent excessive hardening in the HAZ.
Yeah, CEV carbon equivalent. It's basically a number calculated from the steel's chemistry that gives you a really good idea of its hardenability, how likely it is to get hard and brittle if you cool it quickly. And 0.48, that's getting into territory where you definitely need to pay attention. It indicates significant hardenability.
Right.
So when you weld, that area right next door, the HAZ, gets heated up fast and then cools down fast. With a higher CEV steel like this, that rapid cooling is the problem. It can cause the steel structure in the HAZ to transform into very hard, brittle phases, like martensite. That makes the HAZ prone to cracking, reduces its toughness. Preheating tackles this directly. By warming the plate before welding, you slow down the cooling rate after welding significantly. That slower cooling gives the microstructure more time to form more desirable, tougher structures rather than the brittle ones. It avoids that excessive hardening. Now, option A, driving off moisture, preheating does help with that, and that's important for preventing hydrogen cracking, especially with higher CEV steels. But the primary metallurgical reason for preheating at a CEV like 0.48 is definitely to control the cooling rate and prevent that HAZ hardening.
It's fascinating how that one CEV number dictates such a critical action, but how does an inspector actually confirm preheat is done right on a busy fabrication floor? It seems like something that could easily be rushed or missed.
It's a really critical check, you're right. And inspectors have standard methods. Temperature indicating crayons are very common. They look like wax crayons, but melt at specific calibrated temperatures.
Oh, okay. Temp sticks.
Exactly. Or they might use visual contact thermometers, thermocouples, sometimes even non-contact pyrometers. They need to verify not just that the minimum preheat temperature is reached before the arc is struck, but often that it's maintained during welding, especially for multipass welds or thicker materials. The WPS will specify the minimum and sometimes maximum interpass temperature too. So it's not just a quick check at the start, it might involve monitoring throughout the process. Because like we said, getting it wrong, that can lead to delayed cracking that might not even show up until hours or days later. Very serious stuff.
Makes sense. Constant vigilance needed. All right, final question for today. This one's about material behavior at different temperatures. The temperature range over which a steel goes from having high to low toughness is called the MPLAC options. A, critical transformation temperature. B, ductility dip temperature. C, bimodal temperature. D, transition temperature. Last one, what's the verdict? The correct answer is D, transition temperature.
Right, transition temperature, so toughness. It's basically a material's ability to absorb energy before it fractures, often involving some plastic deformation. Really important for preventing sudden brittle failure. Now, many common materials, particularly the ferritic steels we use a lot in structures, show this interesting behavior change with temperature. At warmer temperatures, they tend to be ductile, tough. They can bend, deform, absorb quite a bit of energy. But as you cool them down, they go through this range, the transition temperature range. Below this range, their behavior flips. They become brittle. They fracture suddenly, with very little warning, very little energy absorption. Think shattering glass versus bending metal. We often measure this using impact tests like the Charpy V-notch test, across a range of temperatures to pinpoint where this transition happens for a specific steel and weld.
Okay, so it's a shift from tough to brittle. Tying this all together then, why is knowing about this specific temperature range so incredibly vital for, say, the safety of a bridge or a pipeline in a cold climate?
It's absolutely critical for safety and longevity. Imagine a bridge component designed assuming it will behave ductily. If the actual operating temperature drops below its transition temperature, that component could suddenly fracture in a brittle manner under load, catastrophically. So inspectors need to understand this concept to assure a few things. First, that the base material selected is suitable for the lowest anticipated service temperature. Second, and this is crucial for welding, they need to verify that the welding procedure itself hasn't negatively affected this property. Welding introduces intense heat cycles, remember. Poor procedure control could potentially raise the transition temperature of the weld metal, or the HAZ, making the structure susceptible to brittle fracture at temperatures it was supposed to handle safely. So understanding and verifying toughness, especially in relation to this transition temperature, is fundamental to ensuring the structure's integrity throughout its life, particularly in colder environments.
Wow, okay, that really puts it into perspective. And that actually wraps up our questions for this session. So we've dug into the plastic state in friction welding, the heat input differences with PF and PG positions, why that IQI is key for radiographic quality, the reason for preheating based on CEV, and now this critical idea of the transition temperature.
Yeah, and you can see how they all connect, right?
Mm-hmm.
Material science, the process itself, how you test it. It all weaves together to ensure weld integrity. It's that deeper understanding, beyond just the terms, that builds real expertise.
Couldn't agree more. Well, thank you for joining us on this first deep dive in our CSWIP 3.1 exam prep series. We hope you found it useful. And here's something to chew on as you continue studying. Think about which of these concepts, friction welding state, heat input control, IQI use, preheating, or transition temperature, might be the most challenging to get right consistently out there in the real world, and how truly understanding that specific detail could be the thing that prevents a major failure. Keep exploring, keep asking why, and keep learning. We'll catch you on the next deep dive.